Okay, so here's number 4. So let me read the problem for us here. It says, let f be the function be defined above. So we have piecewise function where c and d are constant. So we'll treat c and d the same way that we would treat a number. So imagine this is like 3x plus 4 and then x squared, minus 4x, right? So however way you treat numbers and constants is the way that you would treat c and d's. It says f is differentiable. So that means that slope exists everywhere. So if the slope exists everywhere, that also assumes that it's got to be continuous. So it's continuous and differentiable, even though they only say the word differentiable. What that means is that if it's continuous, first off, that continuous portion is the fact that these two branches, they must meet at 2 with the same y value. So that means we can set the equations equal to each other because we know that they must share the same y value at x equals 2. So that's one piece that we can use to move through this problem. The second is that if the function is differentiable, that means the two graphs are not only going to meet, they're going to meet where it's going to be a smooth transition from one graph to the next, and there's not going to be a sharp turn. The slope between it'll be the slope from one graph to the next will be the same at x equals 2. So I'm not drawing the graph exactly correct, but it's the idea that the two graphs are going to meet where they share the same slope.
The limit as x approaches 2.
Or I guess we can say that the limit of the derivative as x approaches 2. But we can make it even easier and just say, well, I can just set the derivatives equal to each other. Just find the derivative, set them equal to each other, and that will give me a second equation to work with. Because we have two unknown values we're looking for, having two equations set up can allow us to solve for those missing values. So if we find the derivative for cx plus d, what's the derivative of cx plus d? C, just c. What's the derivative of x squared minus cx?
2x minus c.
Yeah, 2x minus c. So if I have the derivative set up, replacing x with 2, because we know they must share the same slope at 2, and if we can set the equations equal to each other and replace x with 2, this before the derivative, we got 4c plus d equals 4, which still requires some additional information. We have too many unknown values, but if we set the derivative equal to each other, we solve for c, we get c equals 2. If I have a c value, I could plug in, solve for d. D is -4, so 2 minus 4 is -2. Yeah, so that's the strategy with these problems. If they say differentiable, they're kind of hiding information, not hiding, but they're not saying continuous as well. So we just have to understand, okay, their two graphs are going to meet at the same y value. They will also meet with the same slope at that point. Okay, look through pages 1 through 8. Any other questions? Any other problems that you want me to go over with you?
Yeah.
Okay. Problem number 10. Yeah, 10 is that's a little messy. Chances are your AP problem won't be as messy as this. So, yeah, it's not going to be as messy as this. But I guess the big idea here is that we are going to go through to find the second derivative. We first just go through chain rule, right? So tangent of u is secant squared u times u prime. So that's fine. That gets us to this stage. And then from here, we have to go through product and chain. So f prime g plus f g prime. And that's going to be one big mess. But to get to where the answer choice is going to match, what we're going to do is we're looking at what we have here and what we have here. And we're trying to decide, okay, what is a common factor that we can take out of both those extended expressions? So what we can take out of both is we can take out 4e to the 2x. So that's something that we can, well, sorry, this is my cleaned up derivative there. I can take out 4e to the 2x, so that's something that I can factor out. I can also factor out secant squared e to the 2x. That's also I can factor out. But if I factor that out, I'm basically dividing both of these by my GCF. If I divide by my GCF, I'm still left with a 1, so I don't want to forget about that 1 there. And if I factor this out, I'm left with 2e to the x times tangent e to the 2x. So that's why that 1 is there. And also, to convince us, we can also distribute this through the bracket, and we should be able to get back to where we had the line before. That answers your question.
Yeah, thank you.
Anything else? Pages 1 through 8.
Can you do number 11 on page 7?
Page 9.
Page 7.
Oh, page 7. Yeah, this was a little bit tricky. So number 11, right? This one. So we're looking at the second derivative table. It says which of the following must be true. And this is what we probably are going to come. This is probably our first instinct is looking at this and say, well, let's say this is point of inflection at 0 because the cavity is 0 and to the left is +5 and to the right is -7. But there's no guarantee, at least not with this table, with this limited data, that the graph has a point of inflection at x = 1. Because what could happen is that maybe the graph hits 0, but then it bounces up to positive, and then it doesn't change sign until somewhere between 1 and 2, like 1.5. So maybe if a graph looked like this, then there's no point of inflection here because the concavity doesn't change from positive to negative. So this is kind of tricky, right? I think normally we would say, you know, chances are this is the point of inflection, but because there's not enough data here, we don't know what's happening between 0 and 1 and 1 and 2. This is what the graph could look like. But we do know that there must be a change in sign somewhere between 0 and 2 because we're going from 5 to -7. So there's got to be a change. We just can't guarantee it's going to be at 1, even though it kind of tricks you into thinking that it has to be at 1, but it doesn't have to be at 1. It can be anywhere between 0 and 2. Good. Any other questions? Pages 1 through 8.
Someone, I have a question on page 9.
Yeah.
What's the first question? Like do trapezoidal type of sum. Like, what are the steps?
This one here?
Yeah.
Or, okay, yeah. Oh, well, it's only asking for trapezoid approximation. And it depends if your graph is so the graph that is shown to us is concave up, right? Right, concave up. So if you draw a bunch of trapezoids, all you're doing is you're connecting between the tops of every line here. And if you look, because it's concave up, all my trapezoids will be slightly above my graph. So it's gonna be a slight over approximation.
So how do you like know like the points, like where to put those points? Is it on the line?
Yeah, right here. I'm just connecting the dots with straight lines.
Okay. Okay.
And those are my trapezoids. Likewise, if my graph is concave down, then every trapezoid is going to give me a slight under approximation. Because all my trapezoids are lining up below the curve.
Okay.
But either way, trapezoids will be better than rectangles because the way that it's shaped is there's not all that gap. Between the graph and the geometric shape.
Does it appear often on the exam trapezoid? I haven't seen much.
Yeah, as far as Riemann sums go, yeah. Right, like we have to, if we want to find the area of trapezoids, it's 1/2 with height 1 plus height 2. We've done that, yeah. But as far as seeing it on the graph, graphing it, this is as much as you need to do, just knowing that is it going to be over approximating or under approximating, and that it's better than either left or right Riemann sum. Assuming we have the same number of subintervals. Okay, so if you've finished 1 through 8, then today you're going to be working on pages 9 through 16. Yes, it's
An equation equal to 0. Can you remind me how to put it on the?
which page?
Page 11.
Which problem?
On the left, setting it equal to 0 and getting that value. On the left,
It's right here.
very left.
Oh, that's right here.
Yeah.
Yeah, so what we can do is, all we're doing is we're graphing this function, just you put it in, into the form and then just graph it, look for the x-intercept.
Got it. Okay, thank you.
Yeah, use x for your variable.
And then can you remind me of how to get out of, like, how to get into the R, like,
Yeah, so, you're gonna go to mode. Then you're going to, click on function.
yeah,
And then also, if your format is, if you go to format and if it's in polar graphing coordinates, then you want to do the rectangular graphing coordinates. So do second zoom, make sure you're in rectangular coordinates. Yeah, I mean, if you're graphing a polar function, you may want to adjust your format to make it polar coordinates. Otherwise, it'll give you x and y instead of r and theta. So this is second theorem. Second theorem. That's, I want to find. So I have like derivative of 0 to 0 plus the h.
Why should do 1.8? Or does that matter?
Yeah, the one doesn't matter.
Okay.
So I'm just making it up times. Oh,
Oh, it's software bounce derivative.
that round to it's not with the side because there's no chain rule. We're not doing, we're doing rid of integrals, so that's gonna wipe this out. There's no derivatives that impacted.
So like, what do I do if this was like in the bottom, like the thing that we're using?
If it was like 1 plus h is 0,
Yeah.
1 plus h to 1, and then I can flip it. So just to make sure I pull the negative bound. I can always flip the bound and change the negatives.
Or what if there's two functions? Yeah.
Like that, then I'm gonna do it twice. I'll do,
It's just the.
I'll do f of p of x, p prime minus f of q of x.
Oh,
I can repeat the process with.
that makes sense.
I looked at mine to point where they intersect. How do I do that?
Remember how to do that?
I just traced it and estimated, like looked at it.
I tracked this one.
Oh, we did. That's how you find.
So, what I did was I set the two equations equal to each other.
Okay.
And try and find the value. And then it's 0. Zero.
Yeah.
It's kind of confusing, but it's.
And then polar is always gonna be a little bit more difficult. So what I did was I went back to rectangular And I just look to see where this graph crosses the x-axis. And then use that x to have my.
The one that's like.
Okay, well, you keep going.
Oh, that's.
Yeah, so then.
I, for some reason, and tell me just where I'm going off. Said each of these functions has separate properties, but you can only do that for multiplication, right? So you take one function, and I can sit there and then the other one, say, that's five.
Right, yeah, you can't do that with functions.
That's the plus,
Right, so then,
Oh, like, why did they add up to get to zero?
You knew that. Get it up.
so,
They would only,
I'm going to go back to rectangular. I'll go sine of 4x.
Like what?
Because it's just weird, polar. And then I just go to
Genuinely, I would
I
like.
have to look for an x-intercept. That x-intercept is like my theta, which I can go back to. But you estimated it
that's one that they've given us.
on the exam. Yeah. But, I mean, if whatever estimation you got, I'm still going to let you use that as partial credit.
I don't know, can be applied.
Okay, so I actually.
What happens is part B that takes your answer. from
So
that.
actually, it won't be fun.
But you use that wrong answer for part C.
Yeah, so that's importing, and the graders are instructed to look, if it's an importing question, and your answer is wrong because you got bad data, but everything's right, then you shouldn't lose any points in that section. Yeah.
Well, I can try to like. I plug it in. Yeah. So it's like, it didn't really. No, you have to make sure they're not, so you can see. No. Look at it, you know, pretty bad. And I was like. I'm pretty sure it worked. Because I like calculated it, I solved it. And I solved it. Like, I don't. They're like, I use